TCP/IP was designed around 1980. It means it's a technology that is 40 years old. Its demise has been prophesied frequently, as we've noticed previously. However, it still survives. And what we need to look at is why that is the case. In IT, it is rather strange for a technology to survive such a long time. And in this video, we will look at the reasons why this is the case. These reasons also have implications for future developments, so it's not only a lesson in history. The major reason why IPv4 was able to survive so long is the use of a technology known as network address translation. And in this video we will have quite a lot to say about network address translation. There's a secondary reason that we also will say some things about, and that is the use of tunnels. Tunnels enables IPv4 to connect to IPv6 machines, and therefore means they are not outcasts in an IP6 world. Let's look at network address translation in a bit more detail. When one connects to the internet, something like the following happens. So there's the internet, big internet out there, and here you are possibly an individual, and there in the internet you will have an ISP, and you will use your connection, a dial-in connection or a permanent connection, optical fiber, radio wave, cellular connectivity, whatever. And in that way you connect to the internet. Now when you connect to the internet, the ISP assigns a public IP to you. So you get a public IP in a process that works more or less like the DHCP, and therefore you have an address, and whatever services are out there on the internet, you can access using this public IP, and you can talk to the server out there, and the server out there or the service out there is able to talk back to you. Problem comes in if you become a somewhat bigger organization or even have a bigger home network. So what will happen in this case is that your own network will be at the bottom here, but the ISP will only assign a single IP address to you. With all your computers that are situated all around your private network here, if you want to get public IP addresses for them, then that's become an impossibility. Scarcity of IPv4 addresses just means you can no longer do that. But what you can do is to use one of those private address classes. Let's say I use 10.0.0.0, and I assign private addresses to all of the machines in my company, in my institution, in my home. They can talk to one another, but the problem is that these private addresses are not routable via the internet. So they cannot talk to the outside world. What I do, however, to fix this problem is to insert a NAT box or a NAT router at that point. On the outside, the NAT box has a public address. On the inside, I connect it to my private address that I'm using. So it's got a private address, and then I set it up such that this is my default gateway. So any machine that wants to talk to the outside world will simply talk to that NAT box. And the NAT box then does network address translation. More specifically, what it does is it takes your private address, it changes it to the public address, And then the public address is used to send out the request to whatever service you want to access, and the response is sent back to this NAT box, and the NAT box does the translation in the reverse sequence, and it comes back to your machine. To make this a little bit more concrete, let's say that I want to talk to some public service out there. Let's say I want to talk to 8.8.8.8. That is a public address that we all know, Google's public DNS server. And I am at the bottom here, and I'm sitting at the machine that I have called 1.1.1. So there's my computer, and I want to talk from it to that Google server out there on the public internet. What happens is my message or my request that I'm sending from this machine will be sent to this NAT box. It may even be routed internally. If you've got internal routers, then it may be routed, but eventually it gets to the NAT box. Now, for the sake of illustration, let's say that you are sending a packet where the source address is 10.1.1.1. The destination IP is 8.8.8.8. Let's say your port, your source port. In general, when your machine sends out a request, it picks a high order address, one of that pool of high order addresses that are available for you. So let's say the source port was chosen to be 55555. And the destination port, we are assuming that this is a DNS request, so the destination port of what you're sending out here goes to 53. When it gets to the NAT box, it changes the source address to, let's say that public address is just P, for lack of a better choice, a specific choice to use. Let's say it changes the source to P. The destination remains what it was, 8.8.8.8. The source port, well, the NAT box now finds an open port. And let's say that the NAT box decides that on its outgoing interface, there is a port, let's say 123, that happens to be available. So it changes the port to that, and the destination remains whatever it is. And it records these changes that it made. In other words, that change there and that change there in a table. So it's got some sort of a translation table, and in the translation table it records that it's changed 10.1.1.1 port 55555, that it changed that to P port 123. And now this message that goes out on the internet here is one that has a source address P, which is a public address. It's still going to the same machine. It has a new port associated with it, a new source port, but it's still going to the original port that we indicated. So when it gets to that machine answers, responds to the query, and it sends it back. And it can send it back because the source address now becomes the destination address, and that is a public address. It's the public address that was assigned to us by the ISP. The fact that it's now coming from that source port makes not much of a difference. The fact that it's going to that source port doesn't make a difference. When it gets to this NAT box, the NAT box will see that it's supposed to go to P. The NAT box will look this up in its table, and it will see, okay, where I used P combined with port 123, it was actually 10 connected or combined associated with port 55555. So the NAT box will know that this is supposed to be delivered to that machine on the inside of my network, and it is supposed to be delivered to that port on my internal network. It doesn't have to translate the public values that I used initially. That was never changed. It's only the source values that I used when the message was going out that would change to some public value, and then that was relayed via the internet, and it could be relayed back via the internet, and then it gets translated and it gets delivered on the inside of my network. In principle, using this class A address on my network means I can use 2 to the power 24 hosts on the inside of my network. That is about 16 million if you think back to a previous lecture. There is a little bit of another constraint. If every host that goes out gets associated with an outgoing port, I only have 65,000 outgoing ports. So I can't have all 16 million machines talking via their own ports if there are only 65,000 ports available. However, what I can do, if I am really that big, if I have millions of computers, then what I can do is I can get a second public IP address, let's call it P2, and that can be associated with another 65,000 ports, and I can get more and more public addresses. Now, the scenario where that becomes likely is where my private network here is something like a cellular provider. And the cellular provider may have millions of users, and they may all be assigning them to, let's say, public address 10. And many of those users may be active on the internet at any given time. So they, in fact, cannot use a single pipe to connect them or a thin pipe. At the very least, they will use a thick pipe for that connection, in other words, something with a high bandwidth. But it will also use multiple public addresses that are associated with that point so that it could service all, or so that it is able to provide all of the users on the inside of the network with access. This has been the case in countries where cellular phone usage was prevalent long before it became prevalent in our world. In Japan, in China, those countries had a scarcity, a real scarcity of IPv4 addresses and a huge take-up of mobile technology. And they very early realized that they needed to switch to a model where they assign private addresses to their internal users and then connect using only a few public addresses to the rest of the internet. So this is a technique that is rather old already, works very well, except in one or two circumstances that we will look at next. The problem that one faces if one uses network address translation is that one's machines are not exposed to the internet. Because they are using private addresses, no one can access them. And that, to a large extent, is a security benefit, because in general, you don't want the world outside to be able to access the computers on the inside of your network. However, there are exceptions. You may have a web server or a file server or a media server, some sort of service that you want to share with the world. And how do you handle that in the case of a NAT scenario? So let's look at the picture of a pretty similar situation to what we had a moment ago. But the difference here is that I have a machine on my network, and let's say that is my machine. I'm going to call it www, and its address happens to be 10.1.2.3. So that is a private address, and someone on the internet there who wants to access my web server cannot do it because they are unable to connect to a private address. The solution here is what is known as port forwarding. The logic of port forwarding is, in essence, that I set up a port on my NAT box, so somewhere there, and I say relay messages that are incoming on that port to a specific machine on the inside of my network. In other words, suppose I want any request that is intended for my public address, port 80, to be relayed to my www machine. I will have a port forwarding table, and in the port forwarding table I will say if anything comes in on port 80, in other words, on that public address, that's the only place where things can come in, that's the only place that is exposed to the internet. So if that comes in on port 80, then I want that to be relayed to 10.1.2.3, and let's say my web server on the inside is also running on port 80. So that is an example of port forwarding. With the web, it may make sense to use a technique like that. We use a standard port, port 80. In other cases, if I've got some media server, I store all my music or whatever, and that happens to be 10.10.10.10, I can say, well, I'm going to pick some random port 456, and if anything for port 456 comes in, it should actually be sent to 10.1 or .10.10.10, and the port on which my media server is actually running. I've sort of alluded to that value as being a secret, and we know security by obscurity never works. The point is rather that I can forward any port to any machine, any other port, or the same port on the inside of my network. So this solves both my problems. With the outgoing messages, the NAT box just translates them to a public address, and for the incoming messages, I can selectively forward ports to the appropriate machine on the inside of my network. So thereby I can expose at least a few machines to the internet. Another technology that allows us to keep using IPv4 even when we want to access IPv6 machines or services is the notion of tunneling. Tunneling has a much wider application than just what we will see in this example. Sometimes people traffic, let's say, DNS traffic via HTTP. And there are many reasons why people want to do that. We're not going to go into those reasons. But in a nutshell, tunneling is when you encapsulate one traffic type in a traffic type that looks or that is of a different type. More specifically, what we're going to do with tunneling here is to put IP6 datagrams into IPv4 packets. To use this, we will look at a scenario where I have an IP address and I want to use some service on the internet. I may be sitting on my own out here, or I may be inside my own organization and there may be network address translation going on. It doesn't matter. The problem that I have here is that I have an IPv4 public address and I want to access a service there, and that service has an IPv6 address. So I cannot directly access that service because IPv4 and IPv6 are incompatible. What I can do, however, is to find someone who is willing to tunnel this traffic for me. And then I can, and so this service that's willing to do the tunneling for me will have an IP version 6 address, public IP version 6 address, but it will also have an IP version 4 address, public IP version 4 address. What I will do then is to take my message and I will build up this IP version 6 datagram. So somehow that is IP version 6. And then I will encapsulate it. In other words, that IP version 6 datagram becomes the payload of an IP version 4 packet. So there's a header, it has an IP version 4 value, and I can now send this message to that machine's public IP version 4 address. That machine strips away the IP version 4 datagram and it uses the IP version 6 address that I've put in there, and it sends out my message to that machine or that service that I want to access. Obviously, it has to, again, keep in mind what ports and things it's using, so that when that machine responds and the answer arrives at this tunnel entrance, then it can encapsulate the response again and send that back to me. So this has played a far smaller role in keeping IP version 4 alive. But what we will have on the internet is a set of IP version 4 machines, probably very expensive, specialized equipment that is only able to talk IP version 4. And with a solution like tunneling, we can enable those machines to keep accessing services even as the address space moves over to IP version 6. In times not too long ago, we would have spent quite a long time talking about 64 and Toledo tunneling and how one determines addresses for those tunnels. However, we don't have time to talk about that in detail. This is the point at which we leave the Internet Protocol, because once we go below the Internet Protocol, we are not talking about the Internet anymore. We are talking about one machine that talks to another machine that is directly connected to it. There's no routing involved, so things like the Internet Protocol, which has a primary function of routing, is no longer relevant. So this is a good opportunity to pay homage to those who made it possible. Perhaps the two greatest names in the internet are Wintensurf or Wintsurf and Robert Kahn or Bob Kahn. They started working on the internet way before it was known as the internet, back in 1969. They have earned the title Fathers of the Internet. When people use the term Father of the Internet in the singular, then they probably refer to Wintensurf, because he is generally known as the father of the Internet. Bob Kahn did as much work, but led a slightly less public life. Wintensurf is, till this day, busy promoting the use of the internet.
Out of that debate and discussion came some fairly straightforward concepts. One of them was the notion of layering, which we had learned in part from the earlier network, the ARPANET. When we built the various protocol structures, we built them in layers. I think of it as a kind of a staircase. Each layer is another stair step, and if you want to, you can expose each one of those stair steps so that someone can interface with the system at different places in its architecture. The second thing that we realized the need for was gateways linking these different nets together, because the nets didn't directly interwork at all. You needed something that would make them interwork successfully, knew how to talk to each of them independently. We called them gateways at the time because we didn't know they were supposed to be called routers, which we learned later. We learned also that it wasn't enough to define what these interfaces looked like or to define what the packets looked like with their headers and their addresses and the like. We also learned that you needed to have the system sort of self-configure so that it knew what pieces were connected and where. So we had routing protocols that had to be developed as well. I think that almost steered itself out of necessity towards the architecture that we ended up with.
Yeah, I want to come back to this notion of layering because it was one of the powerful insights that we had. It was what enabled us to take advantage of what was out there and build upon it. As Vince said, we had learned quite a bit from the ARPANET experience, but many people think layering is in fact a fundamental notion of what networking is about. Rather, it's a very effective implementation strategy. It's a strategy that lets you do modularization, pull things in, put things in their place, and so forth. But layering is something that is often misconstrued as a requirement. I remember back in the 1970s, the early 70s, the OSI folks came out with a protocol spec. It was a 7-layer specification that nobody ever implemented to because it really wasn't an implementation spec. It was rather a reference model about how you should think about networking. And when we looked at it, they had a lower level physical layer and so forth, all the way up to applications at the top. And Vint and I both took a look at that and he said, well, that's all fine, but where's the internet layer? It wasn't anywhere in particular. There was no internet layer.
Two other names that we should mention at this point are Ken Thompson and Dennis Ritchie for the development of the Unix operating system. While the internet was initially not developed on Unix machines, much of the development work that followed were done on Unix machines. In fact, Thompson and Ritchie were awarded the U.S. National Medal of Technology by President Bill Clinton in 1999. And the contribution that their system, Unix, made to networking was specifically mentioned during that award. All four of these pioneers were awarded the Turing Prize in later years. The Turing Prize is generally accepted to be the Nobel Prize of computing. As we noted a moment or two ago, this is the end of our discussion of Layer 3. The next video will move to Layer 2 in the protocol stack, where we will discuss the data link layer in more detail.